Let's begin Chapter 5. First, we're going to look at Section 5.1 and 5.2, which is an introduction on operation amplifiers, or op-amps is what we normally call them. So an op-amp is an integrated circuit, meaning it's a chip. If you look in your kit, you should have one. It's a black rectangle with 8 metal legs coming off the side. So that's called an integrated circuit. Inside of the op-amp is hundreds of components. And it's things that you don't know anything about right now, and that's okay. We're just going to use it as a black box. And an op-amp really works as a voltage-controlled voltage source. And again, it's not until electronics that you understand why. So right now, just use it, and we'll understand what's in the op-amp later. So first, let's look at the pin configuration for the op-amp. So that's supposed to be a rectangle there. That represents the op-amp. It has 8 legs. And they're labeled like this: 1, 2, 3, 4, 5, 6, 7, and 8. And you know the top, or where the number 1 is, by a little cutout. Sometimes instead of the cutout, you'll see a little circle here. It just depends on the brand who made the op-amp. So the first one is called the balance pin. We don't worry about that. The second one is the inverting input, and we'll look at what that is here in a minute. The third is the non-inverting input. Fourth is called V-. That is a power supply. We have to power our op-amp. 5 is another balance. Again, we don't need it. 6 is our output. 7 is our V+. And then 8's nothing. So it's just no connection, because you don't want to make a seven-legged integrated circuit. That would be weird. So you have the 8th pin. So here's the circuit symbol for an op-amp. It's just a triangle. 2 inputs and 1 output. The inputs are labeled like this: a minus and a plus. You can draw the plus on top, it doesn't matter. Flip it any way you want. So the minus, that is our inverting input. So that's pin 2. The plus is our non-inverting input. So that's pin 3. We have our output, which is pin 6. And then this V- and V+, those are the supplies. So try to keep it consistent with the book here. The V-, pin 4, V+, pin 7. So again, you can think of that as just powering your chip. So an op-amp is supposed to amplify a signal. That's what we're using it for. It can't amplify it if it doesn't have power from somewhere else. So that's where these 2 power supplies come in. They're used to amplify the input and you get something higher at the output. So if our input, looks like this, we expect to see an amplified signal on the output side. These power supplies here are really important. First, if you forget them, this thing doesn't work. Again, it has no power. Second, it has to be 2 separate power supplies. So if you're going to put 9 volts, positive 9 volts here, and negative 9 volts here, that takes 2 separate supplies, or 2 separate batteries with what you're using in your kits. So you need positive voltage here and a negative voltage here. All right, so an equivalent circuit. We can represent this chip, this op-amp, like this. So we call this an equivalent circuit. So the way this chapter works is we're going to look at the hard way to do op-amps first, and then we're going to look at an easier way. And it's really more of an estimate, but it's a really good estimate. So we can represent an op-amp with a single resistor on this side called Rn with a Vd across it, and then a voltage-controlled voltage source, try to keep that clean, with some gain A times voltage VD, and what we call an output resistance, RO. So here's our VO. So this is our op-amp. So in a circuit, wherever we have this, we can remove it and put this in there instead. Because this we know what to do with, right? We've already learned circuit techniques that allow us to solve a circuit that has these components. So we can replace our op-amp with this. Our VD is called our differential output. We'll typically label these V1 and V2. So then VD is equal to V2 minus V1. And A is our gain. RO, output resistance. And RN is input resistance. Now our ideal value for these, what would we really, really like to have? Well, ideally, we'd like to have an infinite gain, right? That would be great. I can put in any signal and get out as much as I want. Not obviously going to happen. RO, my output resistance, I want 0 ohms. So you can think of this as I want no resistance going to my output. I want everything I want out there to go out there. I don't want to lose any voltage here. I don't want a voltage drop. I want everything to go to the output. And my input resistance, you want that really high. So ideally infinite. Because I don't want input signals that mess up what I've set up with my op-amp. Now, that's the ideal. Typical, again, you're going to get something more like 10 to the 5th to 10 to the 8th. Our RO, somewhere between 10 and 100 ohms. And an RN of 10 to the 5 to 10 to the 13th ohms. Supply voltage is going to be, again, supply voltage, these two, going to be anywhere between 5 and 24 volts. Typically we use, I just lost my train of thought. Typically we use 15 or 12 if we're in the lab, but in your kits you're going to use 9 because that's the battery packs that you have. But remember, you have to use 2 separate ones, a plus and a minus. I cannot say that enough. That's one very common mistake. So we're going to do an example problem in the next video that involves a circuit with an op-amp and then using this equivalent circuit in and showing how to solve that problem.